CICU devices.
IABP Physiology. In this animation, we can observe the operation and synchronization of the counterpulsation balloon with the heartbeat. In the following minutes, we will explore the physiology of the intra-aortic balloon pump in detail. The intra-aortic balloon pump operates by inflating during diastole, displacing blood from the descending aorta, and then deflating just before systole, creating a temporary void in the aorta. This mechanism generates its hemodynamic effects, which primarily aim to enhance coronary blood flow, improve systemic perfusion, reduce afterload and left ventricular and diastolic pressure, and consequently lower cardiac workload, and augments the stroke volume. This 3D model illustrates the functional mechanism of the intra-aortic balloon pump, which operates through a precise timing of inflation and deflation. For more information about IABP operation, we invite you to watch our video on IABP Physics. The link can be found in the description. We will now explain in detail each of the hemodynamic effects of the intra-aortic balloon pump. Diastolic augmentation. When the heart relaxes, initiating the diastole, the balloon inflates, causing diastolic augmentation that leads to the following effects. Increased coronary perfusion. The inflation pushes blood back towards the heart, increasing blood flow to the coronary arteries. Coronary perfusion occurs mainly during diastole, as myocardial relaxation allows unimpeded blood flow through the coronary vasculature, improving perfusion. In this part of the cardiac cycle is when the IABP inflates. This way, inflation causes a rise in the aortic pressure that causes an increase in the coronary pressure gradient and therefore increases coronary flow. This effect has already been demonstrated in well-established studies of cardiac physiology. In this graph showing coronary flow throughout the cardiac cycle, we can observe that flow during systole is low compared to diastolic flow, which accounts for approximately 75% of total coronary perfusion. The diastolic flow significantly increases after the initiation of IABP therapy, as shown on the right side of the image. According to the Hagen-Poiseuille principle, flow through a tube is directly proportional to the pressure difference across it and the fourth power of the radius, while being inversely proportional to the length of the tube and fluid viscosity. In patients with severe coronary artery disease, where autoregulation of the radius is impaired, coronary blood flow becomes mainly related to diastolic perfusion pressure. Thus, IABP therapy should theoretically produce a greater increase in coronary flow in these patients. Improved systemic perfusion. Beyond coronary benefits, diastolic augmentation also enhances systemic circulation. The increased pressure in the aorta during diastole improves blood flow to other organs. Additionally, IABP counterpulsation contributes to a reduction in systolic blood pressure due to balloon deflation before systole. While systolic pressure decreases, the greater rise in diastolic pressure results in a maintained or discrete overall increase in mean arterial pressure. Systolic unloading. As systole begins, the balloon deflates rapidly, producing a temporary vacuum effect, generating the following benefits. Afterload decrease. IABP reduces afterload by decreasing the resistance against which the heart must pump, thereby lowering left ventricle systolic pressure and left ventricular and diastolic pressure. This afterload reduction allows for more efficient ejection of blood and increasing stroke volume by 10 to 20%, and subsequently leads to a modest increase in cardiac output, estimated at approximately 0.5 to 1 liter per minute. Interestingly, this improvement is achieved without directly increasing the heart's contractility, unlike inotropic medications. By reducing resistance, the heart requires less energy to eject blood, leading to decreased myocardial workload, and consequently, it induces a reduction in myocardial oxygen consumption. This way, IABP enhances the myocardial oxygen supply to demand ratio by simultaneously improving coronary perfusion and reducing cardiac workload. The effects of the intra-aortic balloon pump can be clearly observed in the left ventricular pressure volume loops, as we will see next. With IABP deflation during systole, afterload is reduced, making it easier for the left ventricle to pump. This results in lower myocardial oxygen consumption and a larger stroke volume. Finally, the device exerts its effect during diastole as well, since the left ventricle remains less loaded and end diastolic pressure is lowered, factors that enhance coronary perfusion.
If you've enjoyed our video, please press the like button and subscribe to support us so we can continue creating quality content like this.